Okay, so hi, my name is Scott Meredith Jones. I'm a lead control and automation engineer working out of Newtown. For those that haven't kind of worked with me in the past, I've been with Control Techniques for 25 years this year, and I started my path with control and automation something like 17 or 18 years ago, working with Kevin Manton. So let's get on with the subject in hand. So today, this particular presentation is to do with PLC Controlled Motion, which is a sort of useful new control interface for third-party PLCs. It's not entirely new. You know, there were predecessors to this. The one that was used in the US in particular was done by Mike Durden, and there was another sort of similar one done by Leroy Samer in France. And what I've tried to do with this particular project is take all of the elements that were useful in both of the implementations and bring them together into one sort of sitting, and then multiply it out for other PLC types as well. So we're not just considering Rockwell, we're considering Siemens PLCs as well. So let's check out the presentation and take a look. So Control Techniques drives, you know, certainly in the past, you know, we've certainly done our best as a company to make our drives sort of compatible with third-party PLCs. So, you know, Profibus, DeviceNet, Ethernet IP, Profinet, implementing those interfaces. Okay, so we've got a good level of connectivity with third-party PLCs, and to sort of help Control Techniques products be integrated into projects where you know, a particular system integrator or a particular OEM has to use a particular third-party PLC, like a Allen Bradley Rockwell or a Siemens PLC. You know, quite often the customer will specify that that's the PLC that they want because they've invested time in training their maintenance staff for how to use that particular environment, so they kind of have no choice. So what we want is to take globally a bigger share of that type of business, and to help us take a share of that business, make it much easier for people to integrate Control Techniques drives into those third-party environments. Okay, so that's the background reason for why we've chosen to sort of centralize and produce PLC Controlled Motion. So what is PLC Controlled Motion? Well, essentially it sort of splits into three offerings. Okay, so we have a plug-in for Connect. So as long as you're running version 2.11 of Connect, you can install this plug-in. Gives you a nice front end to be able to set up the drive side of the application. Okay, so how to set up user units, the motion controller inside of the drive, if that's what the motion interface that you've chosen to use. We've got a comprehensive set of PLC motion interfaces for your given environment. So for TIA Portal for Siemens, and in RS Logix or Studio 5000 for the Rockwell type environment. And for each of them, no matter which one you're choosing to use, there's full step-by-step documentation. I mean, it's screenshots. Everything is totally step-by-step. So not only should you guys be able to get going with it, but it should be fairly easy to help your customers to get going with this as well. So after you've installed the plugin, and we're going to cover the physical installation later, so there's probably about 30 minutes of presentation, and then the rest will be actually showing you how to do this stuff for real. After you've installed, what you'll find is that PLC Controlled Motion appears as something that you can do under the setup menu on the dashboard for the drive that you've actually added. Then what you're presented with is the axis configuration. So this tab is all about setting up the main properties of what you're trying to do with your system. So to start off with, you've got to choose your PLC. So for the versions that are available, you can choose a Rockwell PLC or you can choose a Siemens PLC. In your case, probably it's going to be the Rockwell PLC that you're interested in. Secondly, you choose the control type. So these are representative of the 5 different motion interfaces that you've got available to you within the PLC side environment. Okay, so we've got simple open loop frequency control, closed loop control in RPM, and then these 3 choices at the bottom here, these are all motion controller related. So You have speed control in real engineering units, so that might be millimeters per millisecond, for example. Position control in real engineering units, and EGB for axis following type applications. So once you've selected that, last of all, you're interested in what are the types of mechanics that you're connecting to in your machine. Okay, so what we've got is 3 rotary types, so standard gearbox ratio, belt and pulley, and worm drive. Those are the rotary type mechanical transforms. And then we have the linear transforms, so rack and pinion, ball screw or linear slide, and conveyor. So once you've selected whichever mechanical transform is most applicable to your particular machine, you've basically set up the main properties. One thing to note is that no matter where you are, you'll see this sort of little help icon and libraries and documentation. Okay? It's important to remember, it doesn't matter where you are in the development process, this guy is available. When you click it, you get access to the folder structure for all of the documentation. So as you can see here, this is like a screenshot of the help PDFs for the Rockwell PLC environment, but also you get all of the example PLC code. So when you come to use the PLC controlled offering, PLC Controlled Motion offering within the PLC environment, you need to go and grab your files, put them somewhere that you can understand and then be able to use from the PLC's perspective, because obviously it's a different environment. Okay. So after completing your axis setup, you can see that all these other tabs get formed. So on the basis of the configuration that we've got here, we populate all these different tabs dependent on that. And as you can see, what we've tried to do is actually organize the tabs in a logical order, a kind of commissioning type order. So you can see first thing is set up your motor, set up your option modules, set up your encoder, then setting up the mechanical transform, setting up hardware limits, setting up brake control, so that's both regenerative energy brake and resistor setup and mechanical brake setup. For the Rockwell environment, you've got 4 dedicated cyclic input mappings and cyclic output mappings, so that you can sort of customize your application depending on what you want to do, so you can get extra data to the drive and from the drive. Dedicated units tab, RTMOE setup, so we're using RTMOE to sort of send and receive real-time synchronous cyclic encoder data, so that you can do a sort of leader-follower type application. And finally, we apply the setup. So I'm just going to quickly go over each of these. So motor setup, you can see that you've got the ability to choose between one of 2 motor types, because those are the only motor types that we really support for the AC product range. So you can either have a servo motor or an induction motor. Regardless of which one you've actually chosen, you have the ability to directly enter the motor nameplate data in, if you happen to know it, or if it's a Leroy Somer motor for induction machines, or if it's a servo motor, so a Control Techniques Dynamics motor, you can enter in the model number. So for servo motors, for example, you start off with the frame size. So in this case, you can see down here, this is like a 75mm frame size motor. You type it in, and then you'll get a short list, and you'll be able to click and select the motor of your choice. Once you've clicked and selected that, it'll go and populate the motor nameplate for you with all of the correct data. So it's quite a nice feature. Next, you've got your option module selection. So what you can see here is that you've got a dedicated Ethernet connection. Okay, so this is your PLC comms connection, and also RTMO if you want it. You've got the ability to configure a further 2 slots, so that might be digital I/O, comms options, feedback interfaces, whatever suits your application. Next, you've got encoder setup. So whichever encoders that you've actually got, or encoder interfaces that you've got fitted to your drive, you go and configure them here. The one thing to note is that the position loop in this application is always controlled by drive P1. Okay, so if, for example, you go to dual loop configuration here, okay, P1 will still be controlling the position loop, and you'll have a separate encoder to control the speed loop. You can see in this example, this is just a standard single loop setup, so the position and speed loops are both controlled by the drive P1 encoder interface. As you can see, you can go through, set up all of the standard options for that. The thermistor setup, you can set up freeze position capture if you need to. So machine configuration, so depending on which mechanical transform you've actually chosen, in this case it's a simple gearbox, there are various options that relate specifically to that. So if it's a rotary transform, typically it's just going to be a ratio, and you have a number of different sort of user-friendly ways in which you could enter that ratio. So in this particular screen, it's speed ratio, which is a common way to enter your ratio. For linear, typically it'll either be a gearbox plus a conversion from units per rev, so units per revolution, or turn pitch, depending on which transform it is that you've chosen. Okay. Hardware limits. So if you've got physical hardware limits with a switch that looks something like this guy down here, it's a simple drop down, and it's just choosing which of the hardware inputs from the drive are actually assigned to that, and that will actually trigger the hardware functionality, hardware limit functionality of the drive. So that'll either be, in an open loop or closed loop RPM mode, that will just, send the drive to 0 speed, or with the AMC, it'll use the AMC's standard hardware limit triggering features. So brake control. In this case, this is showing the mechanical brake control setup. So this is the sort of reproduction of the timing diagrams from the drive, but you can actually enter in these parameters all of the various setup and timings for when you're handing over control from the mechanical brake to the motor in this region, and from when you're handing over control from the motor back to the mechanical brake at this end. You can set all of those time delays and whatnot in a logical way. Secondly, sort of physically above this section, you've actually got the electrical regenerative energy brake and resistor setup, so you can set up the resistance and the power and the time constant, etc. We'll have a quick look at that later when we're actually using the tool for real. Network inputs and outputs. As you can see, what we've done is we've given 4 dedicated inputs and 4 dedicated outputs. It's not that every application can use this, but it could be that for your particular application you want to trigger a particular feature that's outside of the scope of PLC controlled motion, that's not in the standard offering, and you might want to map an input parameter to that or an output parameter to that. If that's the case, all of your mappings get configured here, and then when you complete the process, you apply the setup at the end, all of these additional mappings will be made, and then the array, which is the collection point for the data in the PLC, will kind of possess these values, or that will be where that you'll kind of enter in those values at the PLC side. Unit configuration. So we've gone to quite a lot of effort, with the unit scaling. I know certainly from my experience, I've been teaching motion control to both CT engineers and external customers for a lot of years, and almost everybody falls down at some point on unit calculation, and by that I mean conversion from things like encoder counts to real engineering units, so millimeters per millisecond, or in the US I suppose it would be thou per millisecond or something like that, because it's an imperial system. But hopefully what you'll see when we get there is that it's pretty logical. If you've got a rotary application, we give you a set of rotary units to be able to select from. You get to choose the resolution of those units. You get to choose the resolution of your feedback with respect to counts in a rev. So, if you've got a 16-bit encoder, that'll be 65536 counts per rev, etc. We give you useful information about maximum, minimum operating speeds. For those of you that are interested, the ratios that actually go off to the AMC, if it's an for AMC-based applications. We also give you the ability to set up the overall maximum speed reference that goes to the drive, and also the maximum speed that gets applied to correct position error. And we'll cover all of those setups in more detail later. So RTMOE configuration. So all of the setup to transmit motion references are essentially for digital locking type applications. So you've got a leader and follower, where the leader of the application is transmitting its encoder reference over RTMOE to a number of receiving followers. Okay, so we're using our IEEE 1588 based synchronous comms protocol to do that. This page makes the configuration for you, and we're going to be using that in the demonstration later, so I'm not going to go into too much detail about the different options. But the basic premise is, when you're using this, it's there so that you can have, for example, a position motion interface as the leader of an electronic gearbox interface. So that's the idea. So if you're doing, like, I don't know, a packaging machine, and you've got a conveyor belt, and that conveyor belt has several sections, you want each of those to be running in position control. And the idea is that you have some sensor at the beginning of the line and a box that's going to come along. It's going to meet that sensor. You want the whole conveyor to come to a stop to allow an auger or something like that to put, I don't know, packing chips in a box or something like that. This system allows you to do that, but instead of having to kind of tail out encoder connections or add extra encoder options, you're doing it all over RTMOE. So it's kind of a low wire count kind of solution to do this. So it's quite nice. Homing. So for applications that do use homing, so obviously it's not there for the frequency applications, it's not there for closed loop RPM, but for those interfaces, so speed, positioning, and EGB, you have homing set up. You have the ability to configure all of the drive side hardware and configuration for the given homing routine that you've chosen. So the common ones are homing to a freeze, homing to a standard homing sensor, or homing to a hard stop, which is kind of what's shown here. And you can see that you've got the ability to go and set up the hard stop torque threshold, because when you're homing to a hard stop, what you're really looking for is to hit a torque producing current threshold. And then usually you have an amount of filter time that you want to see that current for to accept the fact that you've actually hit the ultimate limits. So this is the kind of homing that you would do on a linear axis that's actually been designed for the axis to bump the end as a cost saving, so you don't actually have to have like an inductive proxy sensor or something like that to detect the home region. Then last of all, you apply the setup. So download it to the drive, and then perform your auto tune, and then move over to the PLC. So from the PLC side, essentially we have made all of the interfaces in ladder logic where possible. Some of the more complicated functions have been written in structured text, but there's only kind of one or two of those. The vast majority of it is in ladder logic. When we did the assessment of the market, it seemed like most people wanted to use ladder logic, so we'd continue in that vein. It makes it a lot easier for people that aren't, kind of hardcore programmers programming in, C#, C++. A lot of the guys that will be using this are kind of maintenance engineer type guys at customer sites, and almost all of that type of class of user can use ladder logic really easily. So it made sense just to continue in that vein. So the function blocks themselves, all of these outer function blocks that start with the prefix CTA, they're fully editable. You can go in there, you can edit, you can add, you can customize, you can do what you like, okay? Fully flexible. The core functionality is wrapped up in an inner function block that starts at CTC, okay? So what we've done is we've given you a lot of flexibility to be able to change and modify the interface, but we've kept the core functionality locked up. Now, when I say locked up, it's visible. So the way that we've actually set up the AOIs in the Rockwell environment and the function blocks in the Siemens environment is such that you can kind of see all of the code, even in the parts that we don't want you to edit. You just can't edit them. So you're kind of giving you guys and the ultimate end users some ability to kind of fault find through the system if they're trying to chase a problem, which is quite nice. It's an important thing. So from the Rockwell perspective, we're supporting from version 17 only, and we tried this up to version 32 Rockwell, and it works fine. Siemens, we're operating from TIA Portal version 14, and to be specific, S7 1200s and S7 1500s. Just for you guys to be aware, we're not supporting the older S7 200s, 300s, and 400s. Principal reason for that is that the function block and systems that we've actually developed for Siemens, there are massive changes in the environment, even if you're writing it in TIA Portal v14, between the older series of Siemens PLCs and the newer ones. So we're only supporting these two. Last of all, as a generalization, the cyclic comms update that you can use is a maximum of 100 milliseconds. So you can still get all of this kind of complex, coordinated motion, with the digital locking over RTMOE, because the network that's handling that is totally separated from the PLC. So what we're really doing is commanding the motion controller, commanding the functionality in the drive, and the drive can go and get on with its job at high precision at a high update rate, despite having a relatively low cyclic comms update rate. Okay, that's not to say that you can't reduce this rate, because you can. You can take it down to, I think it's 10 milliseconds for the Rockwell PLCs if you want to. So, as we sort of discussed before when we were looking at the tool, we've got 5 main function blocks available, or AOIs, for the Rockwell environment. So we've got frequency, speed in RPM, speed in engineering units, position in engineering units, and electronic gearbox in engineering units. For all of these, regardless of the third-party PLC environment, so Rockwell or Siemens at the moment, example routines are available to get the user going. Okay, so you haven't got to do all of this from scratch. You haven't got to start off at the kind of basic AOI level. You can import a routine into your program. That's kind of what's depicted here. These are individual sort of get you going routines. Same in both environments. So for me personally, when I get going with this, I can get an axis going probably 5 minutes end to end if I wasn't describing it in the Rockwell environment. The Siemens environment, because it's a slightly more complicated environment, it adds probably another 5 minutes. So it's usually about 10 minutes end to end, something like that for that environment. So not only have we got the motion interfaces, but we've actually got some supporting functionality as well. So for the Rockwell environment, we've got non-cyclic comms read and writes. So let's say you have an application and they really wanted to get a lot of extra data from the drive for some reason, and you've run out of your cyclic links. What you can also do is set up non-cyclic comms reads and writes to the drive. We've put a lot of effort into the front end for this. So instead of having to use the standard Rockwell interface to gain access to non-cyclic comms, we've dressed it up properly so you've got access to slot menu and parameter. So it's a kind of CT-esque way of gaining access to those parameters. We've also got dedicated blocks to allow you to pull out the digital I/O state, general drive status, and AMC status for those motion functions that are actually running on the AMC. So the function blocks themselves, we categorized them, and we categorized them with prefixes. The main reason we actually did this was because in the Rockwell environment, when you go back as far as version 17, it tends to put the AOIs in alphabetical order. So we've got a lot of different AOI names here, and what it did, it would kind of intermingle all of these ones that you're sort of intended to use with a lot of the ones that are sort of underpinning system blocks that you're not really intended to use. So to get around that and to make it easier for you to kind of use, we gave them these prefixes. So the first prefix is CTA, so all of the primary motion functions, so electronic gearbox, frequency, position, speed, ANC, speed and RPM, etc. They have the prefix CTA. Auxiliary functionality, so again, functionality that the user is intended to use, are called CTB, so that's things like your non-cyclic comms, digital I/O read words, etc. And finally, items that are unlikely to be useful to the user but form a part of the sort of motion offering, if you like, the building blocks of the system, are given the prefix CTC. Okay, so those are functions that could possibly be useful, but they're not generally intended for the end user to use, basically. So the AOIs, or function block structure. So the idea, I think I did mention it earlier, is that we have an outer layer. Okay, so in this case we're looking at the positioning AOI. Positioning AOI, this layer, this outer layer, is fully editable. You can go in, you can change, you can do what you like. I mean, obviously, when you do change that, you have to consider, updates, future updates, and that when you put your code into this layer, you should make it a nice identifiable block, so it's nice and easy to copy and paste as updates happen to the PLC Controlled Motion system. And then there's an inner core, which is where all of the main functionality lies. So this is really an interface layer to this inner core functionality. So it means even if you do make your own edits in here, all of the main bulk of the functionality is hidden in here. So you can, in fact, just update this inner core of functionality and get an updated version of the function block. So the motion AOIs, or function blocks themselves, have categorized inputs and outputs. Okay, and these are those three categories: CMD, CFG, STS. So CMD is command. So those are typically Boolean inputs, and those are for major functions, turning major functions on and off. So you can see in this example here, we've got command drive on, so that's enabling the drive, enabling the motion controller for those that are using the AMC, commanding the drive to reset, commanding a motion stop. So motion stop in this case is commanding the axis to come to a stop with perhaps an improved rate, jogging, going to speed, whatever it is, what other functionality that the particular AOI has. Configure, so CFG. So CFG type inputs are all about setting up the properties of one of these command inputs. So as we can see down here, these are the configure inputs for jogging. So you've got configure jog speed, jog acceleration time, jog decel time, etc., etc. Okay. Last of all, you've got status outputs. So these are both Boolean and integer values. So here are the sort of integer type values. So you've got actual speed from the drive, profile input speed, profile output speed, following error. But you've also got Boolean outputs so that you can arrange your ladder sequencing. So for example, you may want to command a jog forward and then understand that the system has accepted the jog forward, so you could check your status jog active to see whether that particular reference is active. Or for example, you could have been running jog, but because of an emergency situation, you've commanded motion stop, and you want to see that jog has been superseded by motion stop becoming active. So a lot of thought has gone into not only the types of motion that you can have, but your ability to be able to sort of programmatically check and sequence what it is that you'd actually like your machine to do. So we'll just take a brief overview of the different blocks, just so that you can kind of see the functionality that you've got. We're not going to go into too much detail here. So the open loop frequency block is called CTA frequency. Okay, this block works with the complete Control Techniques AC drive range. So Commander, Digitax HD, and Unidrive M, because all of those drives support open loop operation. Okay, so because it's a relatively simple method of operation, you haven't got massive numbers of references here. So because this is like, more your kind of general purpose type market. So you've got a dedicated motion stop, so dedicated stopping reference, dedicated jogging reference for manual control. So, a guy sat there with a, button pack manually jogging his machine along. And finally, a running reference for automated control, so more programmatic speed frequency control. So moving on, we move to CTA speed RPMs. This is essentially a very, very similar interface, only it's now closed loop, which obviously means that you can't control a commander drive with it. So you're now limited to Digitax HD and Unidrive M series because those support closed loop speed operation. So all of the same references again, only now in closed speed loop. CTA speed AMC, so this is the first of the motion controller based function blocks or AOI interfaces. Works with Digitax HD and Unidrive M70X. So again, motion stop reference, jogging reference, speed reference, all in engineering units, and closed speed and position loop. So you've got stiffer shaft control for that type of application. There's little difference between this and the previous one. The only difference is now you're working in engineering units and you're closing the position loop. So as you can see, we're sort of progressively becoming more complex interfaces for more complex applications. And position interface, so this is CTA position AMC for Digitax HD and Unidrive M70X. It's got motion stop reference, jogging reference, homing, because now we're considering position. Okay, so we want to be able to home our axis, and we've got 10 selectable position references. So those 10 position references could either be absolute or they could be relative. Each of the individual indexes have their own profile. So, position set point 1 has its own acceleration, deceleration, and so does position 2, etc., etc. And again, close, speed, and position loop. Last of all, CTA electronic gearbox. Again, Digitax HD and Unidrive M. Motion stop reference, jogging, homing, a single position reference this time because we recognize that you're probably going to want to be able to home and then possibly move your axis to a dedicated starting position before you form your electronic gearbox lock. And then the EGB reference, so electronic gearbox locking reference to form your digital lock with PLC selectable position master encoder over RTMOE. So essentially, for those of you that are out there that are kind of familiar with RTMOE, you have a link number with RTMOE. What you're setting at the PLC interface is which of those RTMOE link numbers that you're choosing to subscribe to from the slave or follower. And again, close, speed, and position loop. So this is essentially the end of the presentation section. I just want to highlight some of the benefits that you get with the system that we've got on offer. Okay. So firstly, it's significantly reduced integration times. I mean, if you went to a system of the past and you tried to individually set up cyclic links to be able to manage the AMC, for example, or to manage the drive, there are a significant number of challenges involved with that. And this reduces all of those and gives you a nice common interface that's well documented and means that you can get motion going very, very quickly rather than having to spend hours individually mapping cyclic links. So it's a massive saving in time. Second thing is that with a relatively low spec PLC, so the PLC that I'm working with today that I'll do the second part of this presentation with is an L24ER Compact Logics. It's one of the cheaper end of the PLCs, yet with this PLC I can still manage and control an electronic line shaft type system, so a digital locking system. So it means for your customer, they don't necessarily have to buy, kind of one of the top-end Rockwell PLCs, pay the license fee also for the Rockwell Motion plugins. They can get that going basically with standard Ethernet IP. They don't need SIP Motion. get a nice system going for less. Only one network is required, so just standard Ethernet connection, so it keeps it simple. For those of you that have customers that are system integrators or OEMs that are kind of forced to switch between the likes of Siemens or Rockwell systems, they've actually got a kind of migration path between those two systems by taking on this motion interface, because the way that the interface has been written, although there are differences in the environments, and you can't literally copy from a TIA portal environment application and paste into the Rockwell environment, it's a massive advantage having it so that the interface that you're looking at and the drive that you're looking at are exactly the same between those applications, so you could very quickly port your application between those depending on what the end customer is actually interested in their application. Particularly if you're using M700 fitted with the multi-protocol factory-fitted Ethernet, or M750, which kind of comes with the multi-protocol interface fitted to it. Okay, the beauty of these drives and this interface is that for the system integrator type customer that is working with these PLCs, that interface supports both Ethernet IP, Profinet, SIP safety, etc. So for those guys, essentially, they only kind of really need to kind of learn how to use these two drives, and then they can complete applications with both of those environments. It's quite powerful. It's not for every customer, not everybody has to switch between the environments, but it's an advantage for those that do. It's fully supported, so training and documentation for Control Techniques drive centers. You've got support suite, technical support, fully aware of this, and it's a continuing R&D project that my team lead. It's flexible, so you've got flexibility in terms of the ability to edit some of the outer layers of the motion function blocks if you wanted to, and in terms of the cyclic link mappings. It supports the entire current AC drive range. So it doesn't matter what system that you're doing, providing the technical capability of the offering is within the scope of that system. So you can have very simple axes that, might be blowers in open loop, to more complex things like labeling machines that are being controlled in position mode, for example, and all of those things can be integrated together using this system. So it's comprehensive. And last of all, it's free. There's no license fee for any of this, so it allows you to have this, kind of mid-range type motion, totally license-free. Okay, so that is the end of that section. If you give me a minute, I'm going to swap over what I'm looking at. So let me just introduce. Where are you? There we go. Okay, so this section, hopefully, for those of you that are kind of actually touching, handling the drive, and actually making some applications, for real out there, this should be of kind of more interest. So, as you can see from the web camera down here, this is the setup that I'm using. So you have to forgive me because the video is somewhat delayed, but there we go. So this PLC, this is my L24 ER PC, PLC rather. It's a cheap compact Logix PLC, but as you'll be able to see, you can do everything that you want to do for this application with it. Here, it's a bit difficult to see on the feed, but this is a Digitax HD M750. And then everybody should recognize this guy because they've been out there for quite a long while. This is the Drive M700 demo case. And in my case, I've got a multi-protocol factory-fitted Ethernet module fitted in there. Okay. Obviously, for Rockwell, you don't necessarily need that, but with this same rig, at the drop of a hat, I could swap it over to Siemens PLC if I wanted to. Okay. So the first part of the demonstration is really just to see the installation procedure, and what you'll be pleasantly surprised with is how quick that is, because it's a very light installer. So I've triggered the installer. Got to be version 2.11 of Connect. I've obviously already got that installed. Click Next. Accept that. Done. So that was about 15 seconds, and we're done. So next thing, let's move into the Connect environment. So I'm going to trigger my copy of Connect. Let's give that a moment to start. There we go. Right. I'm just going to minimize this video feed. There we go. Okay, so start a new project and call this Demo USA. There we go. Okay, so I've got a new project. One thing to note about these drives is that both of these drives are defaulted. They're completely box fresh. They have no setup in them whatsoever. There's no IP addresses set up. There's nothing set up whatsoever. They're just exactly as the customer would have them out of the box, only they've been electrically wired up. Okay, so what I'm trying to show is that, you know, for your users that will be sort of experiencing this scenario, this is hopefully the procedure that they can use themselves. Okay, just close that. So what I'm going to do with this setup is I'm actually going to do an EGB type setup, so a digital locking application where I'm going to lock the M700 to the M750. So the M750 will be the follower, and the M700 will be the leader, if you like. Just going to wait for this to. Oh, hold on. You just get rid of that and that. There we go. Sorry, I've just got rid of some of the other network searching so that we can sort of speed the process up. So in a minute, once that's finished interrogating the network, we should have a couple of drives that have no IP addresses set. There we go. So what you can do if you're on a network and you don't actually understand which drive is which, you can use this wink feature. I'm not going to show that now because it would be difficult to kind of see with the webcam, but essentially you click this button and then the network connection lights on the card, on the Ethernet, factory-fitted Ethernet module begin to flash to indicate that this is the drive that you're kind of looking at. In my case, I don't need to do that because I happen to know that the MAC address of my Unidrive M700s is this 888B0. So I'm going to go ahead and configure him. So I'm going to give him an IP address of 100. 100 is a good one to start off with, if you can remember that, just because the default IP addresses that we tend to use for a lot of our products here start off at 100. So if you're kind of going to go for a kind of hello world type application, 192.168.1.100 is a good one to start off with. I'm just going to apply that. And there we go. You can see that the M700 has now been applied with this IP address. I'm going to go ahead and do the other one. I'm going to go for 101 and apply that. There we go. So we've got both drives, M700, M750, both on the network. I'm going to click OK, and those are going to go and be added to our project. Wait a moment for those to become added. Okay, there we go. Those have been added. So I'm just going to name these just very quickly, just so I don't lose my place of where they are. So this is M700. Guy is 750. Okay. So we'll start off with the M700. Bear in mind, what I'm going to try to do this one is set it up as a position axis. Okay. So first thing to note before you start is that we've gone and downloaded our IP address and Ethernet configuration to the drives and it's accepted it, but the offline copy, so the PC tool copy of the parameters for the drive, don't know about that IP address setup. So what I'm going to do is upload from drive. Okay, so that synchronizes what the drive thinks its IP address is with what the Connect project thinks its IP address is. Okay, so those are now together, and we'll start PLC Controlled Motion. So PLC type, Rockwell. I'm going to choose position, and I'm going to keep it in standard gearbox ratio because, you know, if I put this back on again, as you can see, there's no mechanics on the end of this. There's kind of no benefit really with going for anything special on that front. And then I'll click next. Okay, so we need to go and set up our motors. Okay, so he is a 067 EDA, and it is a 3000 RPM one. I'm going to highlight that. What you note is once I've clicked it, it's fully populated the motor nameplate. Okay, so there's no extra sort of steps to be done for that. I'll click next. So for this application, it's dead simple. It's hello world. We don't actually need to add any extra options, but if you do, click down arrow, and then you've got a bunch of different options down here depending on what it is that you want to do for your application. Click next. So for this particular application, we are going to be doing a single loop application. If you want to, you can do dual loop. You can see that when we go to dual loop, I'm just going to temporarily set it up for now. You can see at the moment we've only got two encoder interfaces, so we've got drive P1, drive P2. You can independently set those up, but the key thing to note here is that drive P1 is always for the position feedback and it's labeled as such. Drive P2 is now for the speed feedback. Okay. If we had other encoder interfaces fitted, we would be able to select them from this drop-down. Okay. All of the other configuration required for the dual loop setup is actually made for you beyond this point. So all you've got to do is tell it which encoder it is that you've got, and away you go. But we are not doing that in this case. So let's move on. So in this case, our encoder is a NDAT. It's 5 volt. Let's increase the baud rate for it. We don't actually need to set any of the comms bits or anything like that for this. I mean, I happen to know that this particular encoder is 18, and this one is really 0. When you power on, because you've got auto configuration on, it will actually sort of set it up for you. Other thing of note is that for these Unidrive M700 demo rigs, the thermistor is not actually connected in them. So what you want to do is go ahead and set P1 thermistor fault detection to none. Okay. So you can see when we scroll down, we've got a few other settings. So we've got the ability to choose whether we want to use the absolute or relative information from our encoder. For older encoders, we've got the ability to set up a power-up delay. So something called hyperface encoders from the past, some of the really old ones tend to have quite a long power-up time to initialize. And we've also got the ability to set up freeze configuration. So if you're doing home to a freeze, or you're just simply doing freeze position capture for the main axis that you're trying to control, this is where you'd go and configure that setup. Okay. There's nothing more to do on that page. We'll move on. So gearbox setup. So before, you've got a few different ways in which that you can specify it. Input speed to output speed, revs in, revs out. Tooth ratio, so if you've been in the situation that I've been in, certainly in the past on site, where nobody really knows anything about the gearbox and you've got to try and work it out, and the only way that you've got really is to individually count the teeth inside of the gearbox. You can enter in tooth ratio if you want to. Other thing of note is that although you're presented with integer values here to enter in your gearbox ratio, okay, you are not restricted to integer values by any stretch of the imagination. So the values behind here are 64-bit floating points, so that means that you've got down to 15 decimal places. to enter. So I can do something like 1.23456 and 1.987654, and at the end of it, the special math that's inside of the units tab will resolve this to a 32-bit integer numerator and denominator to set up the scaling for the motion controller, and it'll all be handled for you. Okay. For this particular instance, I'm just going to go and set them to 1 to 1 because we don't really have anything, and there's not really much value in setting them to something else. So, hardware limits. If you note that sometimes I've been clicking next and sometimes I've been clicking the tabs, it's perfectly okay to use whichever method that you like. It won't make any difference which that you use. So this is where you set up your hardware limits. So you can choose where you'd like those to go from. I'm going to choose these two. We're not actually going to use them in this application. Sorry, there you go. Use those two. We're not actually going to use them, but it's more just to show the principle of the thing and how you set them up. Brake control. So dynamic braking resistor for regenerative energy and pumping up at the DC bus. You've got the ability to set up all of the standard parameters all in one page, so resistance, power, thermal time constant, etc., etc. We haven't got one of those in this application, so I'm going to turn that off. It's just for illustration. Mechanical brake control. You've got all of the main features that you can set up. Delay on brake release, delay on brake apply, etc., etc. One thing that's really is kind of what you need to know is that this is the place where you actually set the digital output that you're going to use to physically control probably an interface relay to be able to control the solenoid that physically controls the mechanical brake. So let's set it to that one. You can see that it's nicely labeled PLC Controlled Brake Release. So when you're looking through the parameter list later, you can actually see which one has been assigned. But a secondary feature for kind of more maintenance control type applications is that you have the ability to force the brake. So you can force it to apply, so that's lock the motor, or you can force it to release the motor, and you can command it from the PLC code. Okay, so you can. It's probably a bit difficult for you guys to see maybe, but this says command manual brake force. So for maintenance type operation, maintenance guys, they can go and trigger this. They can, assuming that they've set up their mechanics in such a way that it's safe to do so, they can trigger this and force release the brake to perform some maintenance activity or something. We haven't got any of that on this, so I'm going to choose to disable, just for illustration. So here's our input and output mapping, so we can choose to set that to something. There we go. You've got exactly the same thing for the outputs. I'm not going to spend too much time. Out of interest, all of the other cyclic mappings that are fixed are listed beneath this collapse control. So if you're interested to know which ones are actually being used by the application, you can take a look. But they're collapsed under this control to sort of save confusion, really. So just to present the user with the things that they are actually going to try to use to make their application work. So units tab. As you can see, we chose standard gearbox ratio back here. Okay, so what we have is a set of rotary type units, because standard gearbox ratio is a rotary kind of mechanical transform. So in my case, I'm going to stick with degrees, but because 360 degrees in a rev is pretty coarse, resolution, or there isn't really much resolution there at all, I'm going to choose an extra couple of decimal places. Okay. The other thing that we can do, if we wanted to, is actually increase the resolution, because the particular encoder that's actually attached to this machine is an 18-bit encoder, so I could go all the way to 262,144 encoder counts per rev if I wanted to. Okay. To keep things simple, I'm going to stick with 65536 counts per rev for the position feedback. So the first thing that you're interested in, okay, is if I take this back to 1, you'll note that you get this information box. Okay, what this information box is telling you is that, firstly, your ratio has a very kind of either a very low resolution, so a very high granularity, so 360 increments in one rev is very high granularity. It could also tell you that you've tried to get more resolution than is really available from your encoder, so you've overscaled it. Okay. If you see this warning, it's not that you can't continue as you are, it's just that it would be advisable for you to modify your ratio, because what you'll probably find is that if this message has come on, it means that probably your acceleration or your deceleration will probably be fairly granular, because you've only given it a very granular resolution in one revolution. But you can see, if I give myself a couple of extra decimal places, that message goes away, and because this is the kind of more in-depth session, rather than the basic training session that I've been running, the thing that you're interested in, so behind this collapse control, is all of the values behind the ratio calculation. What you can see is that our ratio is made out of 36,000, sorry, I read that wrong, 36,000 units with a number of encoder counts per revolution of 65536. So basically these two values here are the product of setting up this resolution in terms of the units and setting up the resolution here in terms of the counts per rev. So this is just what your position feedback is actually capable of. Okay. The one thing that you will note is that we have a ratio expressed here. So this is the basically the result of 36,000 over 65536 gives us this ratio. The output ratio gives us this value. Okay, so when that message appears, what it's really telling us is that our ratio is, what you ideally want is a ratio that results in a value that's greater than 0.1 or less than 10 to ensure that you're actually making the best of your encoder's resolution, okay, and that you're not trying to overscale it. Okay. Second thing that you'll notice is that the values being sent down to the AMC don't exactly look like these numbers. Okay. Now the reason for that is that all of the ratios, regardless of what they are, go through a piece of code called a rationalizer. Okay. Now the rationalizer, what it does is it has the ability to convert any decimal value into an integer value, because the final ratios used inside the AMC or the motion controller are lossless integer ratios. Okay. But if you imagine that you've got a number of units per rev that has some number of decimal places, you need some way to effectively maximize the resolution that you've got but still have an integer ratio. So the rationalizer piece of code does that for you. I mean, we're not seeing it in this instance because we've got an integer value over another integer value, and what you'll find is that there'll be some common denominator between this value that converts down to these. It'll probably, I don't know, divide by 16 or 32 or something like that. But just to note that, we've done a lot of work in the background to make sure that regardless of the number of units that you've got in a rev, that it will always convert it back to the most effective integer ratio to give you the best positioning accuracy for your particular system. So we'll move on. So second thing that you want to notice when you're looking at all of this is that these are the minimum and maximum positions. Okay, so as you can see, this is full 32-bit signed range, but note what happens when I change the resolution down. Okay, so what's happening here is that because we've selected a particularly coarse unit, okay, what we have to do internally is we have to take some of the overall position length back in order to make it so that when we send our speed references out of the AMC motion controller, that we haven't got a large gain. So for example, if we look at the values here, we can see that our output ratio, when we've only got whole degree units, is 65536 over 360. So as you can see, that's a gain of 182. So for every 1 unit, we're going to end up with a gain of 182 at the output. So what you'd find is that would be particularly steppy. Okay, it'll be a very steppy kind of output. Okay. Now, what we've done is reduce the range in order to make sure that despite this large output ratio, that the output speed will be nice and smooth. Okay. So I don't want to do that. I want to set my resolution to be well within range. So I've got full position range. I've got a nice number of units per rev. So absolute maximum axis speed and max operating speed. Okay. The thing that you need to pay attention to really is that this 1800 value here is equivalent to 3000 RPM. Okay, so if I go and change the maximum speed reference that we can set in the drive from the motion controller by 1, you can see that it immediately begins to affect these values up here. So if I go back, change that back to 0. So this is 1800, 0.01 degrees per millisecond speed units. Now what we would normally do is we would reserve 10% of the absolute maximum speed range from the motion controller to allow room for the position controller to act. So when the position controller is acting upon the following error, we have a thing called a maximum speed applied to correct the position error. So what we're saying is that regardless of the position error that we might see because an encoder is trapped or it's faulty or it's fallen off or something like that, this is the maximum speed that we will apply to correct that following error. And what we would normally do is set that to 10% of the absolute maximum. So in our case, that's 180. So I'm going to go ahead and set that. So the difference between this number and this number is 180 because we're reserving 180 user units to allow 10% headroom for the position controller to act. Now in the next version of this tool, we're going to make that connection automatically for you, but in this particular version, it's a manual operation. Okay, that's everything for that page. So we're going to move on to the RTMOE setup. So for this particular application, what we're going to be doing is we're going to be essentially broadcasting the master position reference. So I'm going to select yes. And you're presented with this interface. Okay. So for us, the drive P1 position, that's going to be the position information that we're going to be broadcasting to all of the followers in the system, which in our case will be just the M750. We'll leave it with a link number of 100. The thing to note here is that this link number of 100, this is the value that you actually put into the configure RTMOE master reference input on the EGB AOI, in the PLC code. So it's important to remember this number. We've made it the least significant digits of the IP address because typically when you're in the field, most people sort of identify with the drives by the IP address until it has a proper function. So it's just, just seems sensible to give it a default name of that, really. Now, because in my system, this particular drive is at the head of the network, okay? So what we need to do is the drive that's at the head of the network, so by that I mean the drive that is the interconnection between the PLC and all of the other drives in the system, okay, must be put in gateway mode. The reason why it has to be put in gateway mode is because RTMOE uses a thing called VLAN packet tagging, okay? So all of our high precision synchronous cyclic comms messages are wrapped up in a thing called a VLAN tag packet, and particularly for Rockwell PLCs don't play nicely with VLAN tag packets, so you simply have to filter those out from going forward to the rest of the PLC network. So by turning gateway mode on, gateway acts as a filter. What it says is all the PLC comms will be able to make it through the network and back out again. Okay, so the drive will be able to talk to the PLC, PLC will be able to talk to the drive, etc. But what won't happen is that the high precision synchronous cyclic comms messages will only propagate through this side of the network because we've put the gateway here. So it's just a sort of comms filter. Okay, so we'll move on to the homing tab. Now for this particular application, because it's a simple one, I'm just going to choose to use home at current position. Okay, so the idea is that home at current position, you would essentially jog your axis to the place that you want to consider your home point, trigger the home, and then it will consider itself homed. It's like the most simplistic form of homing, and it's conveniently one that doesn't require any hardware. So I'm going to leave it at that. Then we apply the setup. So let's go and do that. So I'm going to choose to download the setup to the drive. So there we go. I'll just pull on the video feed. So that's gone into the drive. Now, I don't know whether you can kind of see there that we've downloaded the parameters, but the drive at the moment is in trip. So the next thing that I'm going to do is I'm going to shut the PLC Controlled Motion tool for that particular axis. I'm going to go online, and then I'm going to reset it. There we go. The feed will catch up in a second. Now it's in inhibit. Okay. So basically what that's saying is all of our encoder setup that wasn't correct before is now correct, and the drive is actually ready now to become auto-tuned. So we're going to go ahead and do that now. So we'll go to auto-tune. I'm going to select rotating auto-tune, then go next, and then I'm just going to close the safe talk off or enable input. So there we go. What you'll be able to see is hopefully the motor shaft turning very slowly there. So this process takes about 30 seconds or so. So we'll give that some time to complete. There we go. That's complete. So I'm just going to turn off the safe talk off, click next, save parameters. There we go. Let's close that. So before we go offline, I am going to choose to do a couple of things just because I don't want the motor to be too noisy. So I'm going to choose to add a little bit of current loop filter, the encoder isn't super high resolution. And then the other thing that we need to do is we need to go and reset the comms interface. Now, the reason why we do it in this sequence, so we download the parameters, we reset, we perform the auto-tune first, and then we perform the comms interface reset, is that once the comms have established, they take over the drive's control word, and the drive's control word is also the thing that the auto-tune uses. So it's best if you do it in this order, you don't have to do something like subsequently disable Ethernet IP to allow the auto-tune to work. Okay, because until you've actually performed the Ethernet interface reset, it hasn't actually taken on board those settings. So we're going to go ahead and do that now. So there we go, we'll lose comms for a second. There we go. Okay. So that's this axis completed from the drive tools point of view. So what I'm going to do is I'm going to much more quickly go through the other axis to get that set up. But just before I go offline with this, I'm going to upload from the drive so that my offline project copy of this is complete, and I can go and refer back to the project if I wanted to later. So I'm going to choose to go offline. I'm going to close all of these tabs. There we go. Right, okay, so I'm just going to fire the dashboard for the M750. So let's begin. Oh, actually, sorry for this one. I need to upload from the drive because what I need to do is actually make the offline project capture the Ethernet settings, our IP address, etc. Begin the PLC Controlled Motion section. So I'm just going to turn off the video feed for the application for now. There we go. Right. So Rockwell again. In this case, we're going to go for EGB, and I will stick with standard gearbox ratio because it makes sense. So this instance, this is going to be a servo motor. I'm just going to go and quickly look at the label for this particular motor, and it is a 55EZ. EZ, 55E. Give me 1 second. Yeah, that's the one. Right. So there we go. So that's gone, updated its details there. So we'll click next. No need to add any option modules for this because it's already got all of the options that it needs. In this case, it's AB servo and it's a 2048 PPR encoder. Doesn't really have any concept of turns, so we'll get rid of that. Go. Nothing else to do for that one. So nothing to do for the gearbox because we're going to stick with a 1-to-1. I'll stick some limits in here. Brake control, don't need to change any of these. Go back to units, so we'll stick with the same units. There we go. We'll come, let me, sweet, want this to be 3000. Go, make this 180. Go to the EGB setup. So in this case, what we're interested in when we follow the AMC slave ratio from the M700 axis, so the master or leader, if you like, axis, we need to input his ratio here. Now, in the future, I'm hopeful that we're actually going to have like a selectable list, but for the moment, you have to copy it. Menu, so it's 1125 over 2048. 1125. 8. There we go. So you've also got the ability to invert the reference if you want to, and you've also got the ability to change the digital locking bands, to suit. I mean, normally these will be kind of okay, but if you've got a particularly low resolution encoder that you're attempting to follow, you may actually need to increase these values to account for the low resolution encoder essentially. So move on to the RTMOE setup. Drive internal Ethernet is okay for this one, and we're going to consume the reference that we were transmitting from the in-drive M700, which is in position mode. So I'm going to go and set it up and say yes. And because this particular drive is downstream from the drive that's at the head of the network, we'll leave it in switch mode, so all of the data gets passed through, including the VLAN packet. So you actually have to have this in switch mode in order that the RTMOE synchronous cyclic comms actually get passed down. Okay, so there's nothing to set there. We'll leave this at homing in current position, and then we'll go to apply setup. So let me just make sure the drive is selected, which it is, and then I'm going to choose to download to the drive. Okay, so I've done that, and then we can go on to perform the auto-tune. Select auto-tune. I'm going to go on line. There we go. So select rotating auto-tune again. Just put the video feedback on again. There we go. this case, it's this big E-stop button. So as you can see, it's just slowly rotating, doing the auto-tune again. This will be about another 20 seconds or so till it completes. There we go. So let's just stop that. We'll save the parameters. Then parameter setup for this. I'm going to set a little bit of current loop filter in here again. So where are we? 12. Let's go and set that up. Make it nice and quiet because it's a relatively low resolution encoder on that one. It's only a 2048 PPR encoder, so we don't want it being too noisy for the recording. And then last of all, we want to go and reset its communications interface. So we need to go to the Ethernet setup and click reset. Okay. So we'll probably lose comms for a second whilst that happens. So there we go. So that drive is now configured, and you can see because I didn't spend too much time talking about it, it was relatively quick. Last of all, I am going to upload from that drive. And there we go. That's that done. So, next phase, let's go and create the PLC project. So, I'm just going to go and start my Computer Studio 5000. So I'll just make a new project. This one, and then I will call it Rockwell Demo USA. There we go. And click next. And my particular PLC happens to be running 24, so I'm going to go and configure that particular version of the Rockwell environment. And we'll give it a couple of moments to start. Take it a little while whilst it initializes the first project. Nearly there. And there we go. Okay, there's our project started. So first starting point when you get into the project is essentially we need to go and set up a comms interface. So the comms interface that we'll be triggering, we add new module. And then you'll be presented with a list that looks something like this. Deselect all the options, select communication, and then we just need to scroll down the list. I'm just going to get rid of the video feed for a second. There we go. So it is generic Ethernet module that we're looking for. There we go. Ethernet module, generic Ethernet module. So click create. And what we're going to do is we're going to set up the position axis first. So I'm going to call it pos. Oh, actually no, I won't do that. We need to start off calling our axis A1_comms, and I will label it position. Now, the reason why you start off with A1 comms to begin with is simply because all of the examples, the example routines that we'll put into our PLC environment in a minute, they all start off with that. So it's very helpful for you to start off with A1_comms. That way, the first example that you do will automatically be hooked up. You haven't actually got to do too much to it. Okay. So we're going to stick in our IP address. So 192.168.1.100. We need to set up our assembly instances. So the input one is 100, output 1 is 101. Don't worry about remembering any of this, because the step-by-step instructions that come in the manuals for this detail all of this. So you haven't got to write anything down. It's all good. So 32 ins, 32 outs. There we go. That's the end of that configuration. I'm quite happy to leave it at the default RPI of 10 milliseconds. That's fine. There we go. That's the communications interface sorted out. So now the PLC knows about the interface to our drive. So let's go for the next part. So we want to add our example routine. I do recommend that all of you start off with the example routines, okay, until you get used to the system and how to manipulate the AOIs. So I'm going to select import routine. And because it's a position axis, I am going to import them. What I will do is I'll show you the full path so you can kind of see where it exists. Okay, so C drive, program data. Bear in mind also for those of you that haven't chosen to expose hidden files and folders, you may have to go to your control panel and show hidden files or folders, or to show you the other way to find it, if you come back into PLC Controlled Motion and then you click on this, this will actually take you out to the folder system. So depending on which way that you want to go, whichever works for you. Okay, so I'll come back to this. So I go add import routine. This is already actually in the correct place for me. So, but I'll go longhand. So program data, control techniques, connect, extensions, PLC Controlled Motion, documentation and PLC code, Rockwell, because Rockwell PLC is what we're doing, and AOI routine templates. Okay, and I'll select position. So that's going to go and import all of the AOIs that are required to make the system work. It's quite helpful because the way that Rockwell have set up their system is such that any sub AOIs that go to form, like an outer AOI, all get pulled in as a result of you dragging in, for example, a parent AOI or a parent routine. So it's quite a nice feature of their system. There we go. When this screen appears, just click OK, and then that will go and add all of the AOIs that is just extracted from that compound file that we clicked before. That to import. And there we go. You can see all of the additional AOIs have all been added to the project. So I'm just going to collapse all of those. I don't really need to see all those. The main thing to note is that the main motion one is this guy, and these other ones down here that are all marked CTC, these are like underpinning things that go to make up this main AOI. I'll collapse that for now because we don't need to see that. So I'm just going to open up our example routine just to give you a sort of look around it. What you can see is that most of the motion inputs are defined by move statements. Okay, the reason why we do this is because we've found in the past that basically you try to go and set up default values, and sometimes that they work and sometimes that they don't. So essentially we force them all the time with a move. So that when you kind of try to do your Hello World application, you're just trying to jog the axis and try to get some motion, but commanded by the PLC, that you've got a fairly sensible value in there that will cause the axis to move. Now obviously, once you've actually got going, you can just go and delete all of these rungs and then start editing directly at the motion interface. So if where are we? There we go. This is the main motion function block, and what you can see here is that our Ethernet module here has the same name here, and it's automatically been connected for you. I haven't had to do anything. You can just call this routine, and it will simply work. Okay, so that's the main reason to remember that A1_comms. So next thing that we've got to do is actually we need to service this. Okay, so what we need to do is go to program control and call a jump subroutine. So I'm going to go and add one of those, and then I'm going to go and add in our example routine. Now the reason why everything has A1 on the end is A1 is for axis 1, axis 2, axis 3. feel free to name it to whatever you like afterwards. It's just so that you understand the reason why it kind of is everywhere. And then I'm going to go and remove all of these unnecessary instruction parameters because I don't want to service those. There we go. So essentially, we're now at the point where the comms is connected, the example routine is in, we're now servicing our example routine in our main operating routine. The last thing to do is actually to tell the project about our particular PLC. Now, the assumption is that your users know how to set these things up. They know about their PLCs, so I'm not going to go into setting up the path to the PLC. I'm just going to choose set project path because my setup already happens to know that, and I'm going to go online. Just going to reintroduce the video feed whilst that's going on. There we go. So I'm just going to choose to download this. Download. What you may sometimes find is if your PLC has already had an established link with the drive before, you may get an Ethernet IP timeout during download, just because you've essentially lost the link from the PLC for a moment. It's not an issue, it's just a fact of the PLC dropping its comms for a moment whilst the download takes place. And there we go. See, I've got one because my PLC already previously had a program running. There we go. So I'm just going to go and reset that. And what you can see is that our comms is working. You can see by this green line that the routine is being serviced, which is good. Let's go into our example. Shall I just shut that just for a second? Scroll down, and here's our interface. Okay, so when you're starting up the Axis for the first time, the things that you're interested in is status cyclic comms, this particular output, green, so it means it's set, indicating that you haven't got an error. You want to make sure that you have no AOI active errors, so that's telling you that you've got no input or output kind of problems to be able to control it. As you can see, this is 0, so that's okay. Now, because we are doing a RTMOE application, it's also worth noting that the status of the RTMOE connection from the perspective of the M700 is shown here as well, so we know that our synchronous cyclic comms are actually working. Important to know. What I tend to do is, before I kind of get going, if I just hover my mouse there just so that you can see, I tend to toggle the STL on the drive. Okay, so what you can see is me toggling the switch, and you can see drive enable coming on and off, and that's a fairly good indication that you've actually, not only is your comms up, but you've got real-time changes sort of happening at your PLC block. So that's what I tend to do. So first thing, we want to command drive on in order to be able to command some motion. So let's go ahead and do that. Now, I don't know whether you can hear over the audio feed, probably not, but I can hear that my drive is enabled. The thing is, you can actually see some of these feedback values moving about. So not that I need to do it particularly, but I'll just choose to execute at home now. There we go. Interesting. So the first thing that we're going to do, let me put the video feedback on, sorry. There we go. Right, so let's just get that Hello World application going. So I'm going to choose to jog. Hopefully what you'll see when the video feed catches up is that now we're able to jog. So we've got our Hello World. We've now got the PLC able to control this. I can kind of stop and start the Axis using the default values in the project. Okay, so that's about as far as I'm going to go in terms of programming something, because we simply haven't got the time to do anything more complicated. So what I'm going to do is I'm going to turn this drive off for just a second. There we go. I'm going to go offline, and now we're going to go and configure the second Axis. Okay, so I'm going to go offline. I'm just going to shut the video feed down for a second because we don't need that. So what I'm going to do, we need to copy the comms interface. So I'm going to copy that. So I'm just using Control-C. I'm going to go and paste that on top of there. So we've got our new instance of comms interface, and then I am going to go into the properties of that comms interface, and I'm going to go and rename it. So I'm going to go and rename that A2, and we'll name that EGB because that's what it's doing. You can see that once you've actually made this and you copy and paste it, all of the assembly instance and size and all of that kind of stuff is already kind of set up for you. So you really only have to do it once the first time that you make the project. In fact, you wouldn't even have to do that if you copied an entire Rockwell program for yourselves if you wanted to do that. So I'm going to enter in its IP address. So in our case, it was 192.168.1.101. And I'm going to apply that. Here we go. And that's done. So next thing is I'm going to go and import the example routine for that. So I'll just minimize that guy for a second, and then we'll go and add that. So add import routine. So in this case, I am going to be adding the EGB routine, okay, because we're going to form a electronic gearbox lock. So I'm going to click OK on that. Just wait for that to go and add. And what you will notice when you add the second one, because this particular routine import does contain some of the same names, you'll get a few of these warnings saying about a name collision. Don't worry about that, just click OK. What will happen is that anything that's a collision, it will just choose to use the original one, and since all of the routines and all of the underpinning AOIs actually use all of the same source ones, it's okay. So click OK with that. So what you can see now is that essentially all we've done is really add CTA, electronics, gearbox, AMC. Okay. There we go, and we've got a couple of release notes in here. So for those of you that are kind of interested in any updates or anything, the release notes are actually embedded into the example releases themselves. So I'm not going to. I have to go in here, don't I? There we go. Right, so first of all, we need to go and reassign the comms. Okay, so this one will be directed to A1 because that's the one that we direct to by default, but we want to go to A2. So I've done that one. Done that one. Bear in mind, all of these steps are documented in the step-by-step documentation with it. So that's all that you have to do. So now this instance of AOI is now linked up to our comms interface down here. That's all that's required. So next thing, we need to go and service this instance. So I'm just going to go ahead and do that. So we need to go to main routine, and I'm just going to go and copy and paste this, and then I'll choose to service it second. I don't think it makes any difference. Bear in mind, in all ladder editors, it tends to work left to right, up to down as a priority. So in my case, I'm not for any particular reason, but I'm just going to choose to service the EGB second. You could do it the other way around if you wanted to, but there's no way to execute both of them at the same time. You have to choose one first and then the other. So that's what I've chosen. That's it. So that's about all that you need. Let's just do a quick check just to make sure that that's okay. There we go. That is okay. Good. So I'm just going to go online. And I'm going to download. So let's give that a moment to download to the PLC. Okay. Yep. There we go. So what we can see is that we've got our comms up. as indicated by this guy up here. We can see that both routines are being serviced, as indicated by this green line here. We've got no extra kind of warning information. So let's go ahead and have a look inside of the EGB. So what we can see to begin with is that our cyclic comms are okay, which is great, but we can't see our RTMOE comms okay, and probably the reason for that is that the default link number, which is here, yeah, you can see that it's set to 0. So let's go ahead and set that to 100. There we go. So there we go, and you can see now that I've configured the link number to actually receive the master data from RM700, you can see that this is now indicating that it's now receiving that synchronous cyclic data. Okay, so next thing, as I said before, I am going to choose, hold on, let me just turn back on the video feed so you can see what I'm doing. There we go, right, so I'm going to go and release this e-stop button, which happens to be controlling the enable. It's not a kind of power off type e-stop in this case, it's just simply controlling the STO. And as you can see here, the drive enabled, if I turn that guy off and on, it's being controlled. Video feed's a little bit behind, I think it's a couple of seconds or so, but you can see me doing that, which is good. Okay, so now we're at the point where we're ready to indicate that we'd like the drive to start. So I can hear that my drive is engaged. So if I can feel that I've got some servo control at that output of the shaft, which is nice. And then I am going to choose to jog forward. So let's do that. And there we go. And what you'll see, there you go, you can see the axis is jogging. So there we go, that's phase 1. So if I turn that off, there we go, so the axis has stopped. So what I'm going to do is I'm actually going to go and open up our position. And just for the purposes of the demonstration, I'm just going to ask this axis to jog. Okay, so I'm going to command drive on. I can hear that my driver's turned on, and I'm going to ask it to jog. So what you can see in the video feed is that axis is jogging. Happy days. So that's the motion reference that we're going to follow. I mean, obviously, if you're going to do a real application, you'd be following something a bit more interesting than just a jog reference. But for the purposes of this demonstration, I think it shows the point. So what I'm going to do is I'm going to go back to the EGB axis. And then in my EGB axis, I am going to command the EGB to engage. There you go. What you should be able to see now is that these two axes are following each other. Now, if I do something nasty to it, like disable this, so what I just did then was disable the master. You can see that both have stopped, so it's showing you that it really is a digital lock between the two. So I've just gone and re-enabled it, and both axes are going. It really is as simple as that. So I think for me that kind of concludes probably the most demonstration I can do in the time that we've got available. I mean, clearly you can see that there's a lot of effort that's gone in behind the scenes to sort of document all of this and make all of these systems work in a cohesive way, in a way that hopefully enables you and your users to be able to use this in a simple way. So for me, that's the end of the presentation. So what I'll do is I'll be happy to accept questions. You might have to give me a couple of moments just to clear up my setup so that I can actually hear what you guys are saying. So if you give me a moment, I'll just disable these two.
Tim has a question. Go ahead, Tim.
Okay, sorry,
hey, Scott,
Tim.
how you doing?
Yeah, all right.
When you're using dual loop, where would you actually set up the ratio between the position encoder and your feedback encoder?
It's automatically done for you. You don't actually have to set it up at all. The only thing that you have to do is judge the resolution of the speed feedback encoder. So the output ratio in the AMC, okay, is with respect always to the normalized position in the AMC for that encoder interface, for the speed encoder interface. So normally that's set up to 16 bits and that's essentially all that you need to do, because the other part of the output ratio, so it's a number of encoder counts over a number of user units at the output, is all handled by the software. You don't actually have to do anything at all. It just manages it for you. So
right,
if I could get my screen, yeah, sorry, go on.
I'm actually doing an application now with that, and it's not very clear on when you're doing dual loop application. Like I have it's like a 50-to-1 ratio between the two, between the master and the feed from the position versus the
right. Okay.
And it's always throwing it back as the inverse of what my slave user units are, which is not correct.
Okay, so let's try and.
So go to your encoder setup and click.
Well, okay, let's just add a drive. I'm not going to go through the full setup. So what are you doing? Are you doing a Unidrive M?
Yeah, 700.
Okay, let's just put it. Yes, can stick one of those in, and then we can follow. So PLC Controlled Motion. Any particular? If you're doing dual loop, you must be in one of these three.
Yeah, do position control.
Yeah. Okay. Position. Oh,
and
what? What transform?
It's actually ball screw linear slide.
Okay. So for the purposes of what we're trying to do, we won't bother changing any of that because it doesn't matter.
Nope.
We'll go to dual loop. So we'll say that it's an AB for the purposes of this.
And that's
we'll
like position feedback is to say SSI.
In all honesty, it doesn't really make that much difference which one that you've gone. I mean, we can put it in if you want. SSI.
No, it doesn't
there we
matter.
go. Yeah, no, it won't make any difference. Okay, so what's your turn pitch?
Of the screw, it's put 667 in there.
Okay, and that'll be, was it millimeters? Is it or?
Yeah,
millimeters. Yeah. Okay.
That's fine.
So we'll go to units, select millimeter units. We will give ourselves some kind of chance of achieving that. There we go. That's a pretty even ratio, which will work quite nicely. So what you can see here is that you've got two sets of ratio set up. You can see for this particular transform, you haven't got any ability to add a kind of output gearbox. So for your application, presumably you have got an output gearbox, which is why you're having that kind of problem. Is that correct?
Yeah.
You've got an out. Yeah. Okay.
Correct.
All right. So let's go and choose a mechanical transform that's both linear and has a gearbox. So if we just choose conveyor, I know it's not the correct name, but it has the kind of properties that you're interested in. So let's what was it, 667 or something like that, wasn't it, that you chose?
Yep.
We're going to go and choose millimeters, and then you are saying it's 50-to-1, is it? Is that correct?
Yeah. Well,
this will be close enough. So.
Yeah. Okay.
Yeah. So
that's fine. That's fine.
The transform is motor 50-to-1 gearbox, so that you got torque improvement to whatever the output load is.
Yep.
Okay.
Yep.
So then we go down to units. I think all of this is kind of correct.
All right. See, that puts them that puts them differently.
Yeah, that puts the ratio in, but that's what I'm saying. If you've got an output gearbox and you're doing dual loop with a ratio in between, you have to choose the conveyor type in order for it to go and calculate it correctly. Otherwise, there's kind of nowhere basically for you to go and set the output ratio.
Okay.
Now,
all right. That's where I was getting lost then.
No, don't worry. It's okay. It's good that you've asked the question, because a lot of people do dual loop and it can kind of get a little bit complicated. But I mean, if you know that you have to use conveyor if you want to do a transform that is linear plus a gearbox ratio, that this is the only way to do it at the moment. I can say that for not the next version that we're pushing out, because the next version that we're pushing out, 1.5, has a load of ease of use features. So the idea is that 142, the version that you're looking at, actually this is 144, so this is the kind of Siemens and Rockwell version. So the version that you guys are officially releasing in the US is 142, so it's Rockwell only. I'm choosing to show you the full version, which you can have for early adopters if you're interested. In the version that's coming, things like the kind of 10% that you kind of leave for speed applied to correct position, that will just like be automatically calculated for you based upon this value here. The feedback resolution will automatically be calculated for you based upon the encoder setup that you've chosen. Yep. The maximum speed reference here will be automatically set. So there's loads of things that we can automatically do for the user to make it easier for them. Secondly, there'll be like point of use help and all of these different places. So instead of having a tooltip that gives you a tiny bit of information, it will be quite a big piece of information that can actually sort of help you practically, from my experience, get these axes set up. So, for the moment, some of these things are manual, and then in the version beyond that, we're going to have a system that allows you to build a machine out of many complex ratios. So instead of having a conveyor, if I come back to this particular mechanical transform, you've got the ability to set up a gearbox, but it could be that in your practical application, that's made out of, I don't know, a belt and pulley and a gearbox and some other ratio. Do you know what I mean? There could be quite a few ratios in there. So you'll be able to build a machine out of up to 5 different ratios and plug them together in a sort of pictorial type editor, and then choose the final mechanical transform at the end, whether it's like rotary or linear or whatever. But for the moment, this is the interface that you've got to do that kind of thing.
Yeah, you should probably almost think about how they did it in MCS with the PLC Open on there. They did a nice job with it. They actually have a tab called Dual Loop on there where you can set that up.
Sure. Well, I mean, in this case, the dual loop part of it's fairly, you're kind of hidden from it in the background. As long as you understand what your ratio is, the tool actually goes and sets all of the rest of it up for you. So you kind of don't need to know how to kind of configure this and set 326 and all of those other pieces. It sort of does it for you.
Yep.
Hi.
Okay.
This is Fitz.
Can I appreciate it.
Sorry. I just have a really quick question. It's more of a curiosity thing.
Sure.
Since we're talking dual loop, so to date I've always used the P1 as my speed and my P2 as my position. Is there what's the reasoning for picking to do it the other way? Because typically
I can answer that question.
Okay.
Yeah, basically the reason why it has to be drive P1 is because drive P1 always exists, okay? And what you need to do when you're setting up your cyclic communications is always have a point for the cyclic communications to route to, so that you can configure from the PLC properties related to that particular encoder. So for closing the position loop, it's the only one that exists all of the time. So 99% of the time when you're not doing a dual loop application, drive P1 is the owner encoder, and it does your speed and does your position loop. But when you open it up, it's basically the low-level reason is we control the freeze setup, and in order to have a fixed cyclic mapping, you have to know the location of the freeze stuff that you're resetting, which means we have to fix it at drive P1.
Okay.
Yeah. Any more? Bear in mind through all of this, guys, that those of you that have actually attended this session, if you've got further questions, you're more than welcome to email me direct with anything that sort of relates to this presentation directly. So if you come up with questions afterwards, give me an email. It's fine. So for those of you that don't know me, it's scott.meredithjones@mail.nidec.com.